Well, welcome back. In this video, we're going to take a quick look at implicit differentiation. This is a useful tool. You may find some instances where you'll find this a useful technique to carry out differentiation. So here we have the equation of a circle, x squared plus y squared is equal to r squared, where r squared is the radius, and we want to evaluate dy dx. And you see that we don't have y defined separately up here. So there'd be two ways that you could go about doing this. I think, just based on what we know up to this point, we would just express y. Now this might not always be easy to do, and that's one of the benefits of doing implicit differentiation, because it may not be so easy to show that, in this case, that y is equal to r squared minus x squared to the 1/2 power. But then we would, we would rearrange the equation of the circle, solve for y, then take its derivative. And then we'd find that the derivative dy dx would be equal to minus x over r squared minus x squared to the 1/2 power. The second approach is to use this approach referred to as implicit differentiation, where we never bother to solve for y. We just differentiate this expression that we have x squared plus y squared is equal to r squared, and we just distribute the ddx operator through the terms in this relationship. So the derivative of x squared is equal to 2x. The derivative of y squared with respect to x, well, it's kind of a dy squared dy dx, so we have to use the chain rule on this part. So we take the derivative of y squared with respect to y, we get 2y, and we have to multiply that by dy dx. Now dy dx is what we're after, so there's our dy dx. And the derivative of the radius, the radius squared is just a constant, so that's 0. And we end up with then 2x plus 2y dy is equal to 0. Rearrange terms and we find that dy dx is equal to minus x over y. So this approach again is referred to as implicit differentiation. We didn't have to go to the trouble of determining y first. We could do that later or not. We distributed the derivative operator through the terms in this relationship, evaluated that, and we found that dy dx is equal to minus x over y. So it quickly leads to this derivative, and then you can solve for y and just substitute into this relationship. So solving for y, we have y is equal to r squared minus x squared to the 1/2 power. Substitute that in. Now we have a dy dx expressed in terms of x. We could also calculate dx dy. So this implicit differentiation allows us to do that dy dx or the dx dy, depending on what it is that you're interested in. So if we take another example just to illustrate this approach, if we have a function which is x squared times y cubed and it's equal to 25, and we want to evaluate dy dx. Well, this is a product, so we're going to have to use the product rule. So all of our rules come into play here. This is just a new approach, a new technique that we can take advantage of. And so in this case, we've got a product rule. So this would be our, we'll go through. I've recommended that you define what f is and what g is, and df dx and dg dx. And so I'm going to leave that to you. But here we have f. Just write down our f here, which is x squared. Then we take the derivative of our g, which is y cubed, with respect to x. And the next term, we know in the product rule, take the derivative of the first term, which is 2x, times the second term, g, which is y cubed. And then this is equal to 0. the derivative of 25 is equal to 0. So when we go through that process, dy cubed dx is equal to 3y squared, and combine those terms, we get 3x squared y squared dy dx plus 2x y cubed, which we can then rearrange to get 2xy cubed minus 2xy cubed over 3x squared y squared. Cancel out common terms in the numerator and the denominator, and that gives us that dy dx is equal to minus 2y over 3x. So, and in this expression, we've never evaluated what y is. We could do that. We haven't had to. We found out what dy dx is. We could also evaluate dx dy, but once we've evaluated dy dx, we know that dx dy should just be the reciprocal of dy dx, and it is. You could work through it, and you'd find that dx dy is just equal to minus 3x over 2y. Okay, here's another example. Might be a little bit more difficult to solve for y in this expression. So implicit differentiation really, turns out to be useful here. We find the question here is to find the equation of the tangent line at a point x1, y1 equal to 1, 1. So I'll leave it to you, but you should be able to use the rules that we've developed to show that dy dx is equal to 5x to the fourth plus 3x squared over 5y to the fourth plus 1. And if we evaluate this expression at the point 1 and 1, substituting 1 in for x and 1 for y, we find that dy dx is equal to 4/3. Well, this is just dy dx is a derivative. It's a slope, so we have a slope equal to 4/3. And we want to know what the equation of the tangent line is. So we don't have another point in this case. We've talked about earlier, in one of the initial videos, we talked about the equations of straight lines, and if you were given 2 points here we've only been given 1 point, but we know that the slope is, the slope of a straight line is equal to a delta y delta x. So y2 minus y1 over x2 minus x1, we know that has to be equal to 4/3. So we've also been given that x1, y1 is equal to 1 and 1. x1 is equal to 1, y1 is equal to 1. So we have a general relationship then. Just kind of coming back over here, we've got, substituting y for some general y2, we have y minus 1 is equal to 4x minus 1. And I've just kind of carried through the 4/3 here, so that we have 4x over 3 minus 4/3. And we can rearrange this as 3y minus 3 is equal to 4x minus 4. And also into a form where 3y minus 4x plus 1 is equal to 0. So implicit differentiation is something worth keeping in your toolkit. It may come in handy. You have complicated expressions like this. It may not be so easy to solve for y. Similarly for this one, you could do it easily enough with this one, but it would be fairly difficult with this expression here. And and here we just carried it a step further and said, okay, well, we're at a particular point. What's the equation of the line? What's the equation of the tangent line? Okay, well, next video we're going to work through some example problems to illustrate the use of derivatives in geological applications. So thanks for tuning in, and see you next time.